I want to talk a little bit about Laplace's equation and examine the charge density inside a uniform conductor that's carrying current. And what we want to show is that Laplace's equation holds inside the uniform conductor which is carrying current. And then we want to find the total charge density rho inside this uniform ohmic conductor that has steady conditions. And what we want to show is that this rho is equal to 0. So what do we need? Here's the current density as a function of the E field. That's just Ohm's law. We will assume no buildup of charge with time, so the current is steady, and we're going to use the continuity equation. For part A, we want to start with the continuity equation and this value of J. So we put in the continuity equation and realize that the right-hand side, which is this quantity right here, will be 0 because the current is steady. In this case here, there's no buildup of charge occurring. So if you have then del dot J equals 0, since J is equal to sigma times E, if you take the divergence of that and set it equal to 0, you can conclude that the divergence of E equals 0. So I think you can see, you start here, you say J is equal to this quantity here, take the divergence, and that's equal to 0, and therefore the del dot E is equal to 0. If you assume that this conductivity is uniform and constant throughout the conductor, we can now start by writing the E field in terms of the gradient of the potential. So that would be minus the gradient of potential. If you take the divergence of E, which is 0, and expand this now, you take the gradient of this quantity. It's going to be del dot, and then here's the gradient, which is E, and just work this out, then it'll be minus del squared of V, and that's equal to 0. If you look at this, that's Laplace's equation. If you come back here to Poisson's equation, which says that this quantity is equal to rho over epsilon naught, this is the charge density, then Laplace's equation and this equation require for those to be equivalent that rho is equal to 0. So that means then when you have charge flowing through the conductor, it does not have a total charge at all. The total charge is equal to 0. So this is Laplace's equation. This is actually part B to find the charge density inside the conductor. I just want to point out, if there is any charge buildup, it has to be on the surface of the conductor. This is a cartoon of what you might see in this case. We have a segment of a conductor, and this is just schematic. We could put it anywhere of any length. We notice before we start conducting particles through this material that the total number of lattice ions is equal to the total number of charge carriers. That means that the rho total is equal to 0. Okay, so we're not running current through this yet. However, if we now start running current through it, you can imagine it as follows: that you have some charge that's just about ready to enter this material, and you also have some charge that's inside this segment that is going to leave. Now I think you see where this is heading. I've also called this segment here charge in waiting because it's going to replace this one. This is the charge about to enter, this is the charge about to exit, and so when you have the time increment that will cause this to change, this is the charge that's entered, this is the charge that has exited, and now we have a new charge about to exit, and we have a new charge about to enter, and if you want to make this complete, we have a new charge in waiting, which will then come up here, and so on. What you're seeing is that this charge here, which is symbolized by this rectangle, is equal to the charge that's left. In no way have you changed the total amount of charge carriers. The number of charge carriers has stayed the same, and that stayed equal to the number of lattice ions, so the total charge is equal to 0, and that leads to this conclusion here. So the net result is the net charge inside the segment stays at 0. If you take the entire conductor and go around the loop, put in a battery if you want, then what you see here is that for this entire loop, this cartoon would actually work, or we can use our equations, and what we conclude is that there's no charge, free charge, contained in this loop. The total charge is equal to 0. Well, what about the E field inside the conductor? So here we have a cylindrical conductor, and we'll allow a current density J be flowing through this conductor. Let's imagine that one end is at plus V0 and the other at 0 volts. The Z direction is in this direction, and we'll have the normal force being on the sides in this direction, and if we wished we could put vectors on the ends. We've already said that if this is the case, rho inside is 0, then we'll end up with the divergence of E inside is equal to 0. And we know then that Laplace's equation holds. The ends of the cylinders are at equipotentials that we show here. So we know the potential on the ends, okay? But what about the cylindrical walls? The first thing is, if we have no charge entering or leaving, then we have to have that the component of J perpendicular to those walls has to be 0. Otherwise, charges would be leaking out into space. If J is given by this quantity here, and we take the dot product, then we'll have, this is the conductivity, and so you'll have sigma E dotted into the n hat, and we concluded that that should be equal to 0 because there's no charge leaking. Well, what that means, if you have this dot product here, remember that this is related to the change of potential in the direction of the normal vector. And that's what this quantity is here. You have the derivative of V with respect to the normal direction increment equaling 0. And that's on all of the side walls. So on the cylindrical walls, where we have this equaling 0, then we have both the potential and or the normal derivative on the entire surface of this volume. Laplace's equation has a unique solution over the entire volume of the conductor. This is a differential equation boundary value conclusion. All we need to do is guess a simple potential that will satisfy these boundary conditions, and it's this potential right here. If you have V sub z equaling V0 z over L, which you would conclude from basically a uniform field kind of idea, so you have a constant potential across a region of length L, and if you put z over L, you'll have then the value of V of z as a function of position z. We've done this before for a number of cases like parallel plates and things like that. Z is measured along the cylindrical axis, and this is in fact the solution because it satisfies the boundary conditions. So all we have to do to find the E field is to take the gradient with the minus sign, and so if we do that, we get this quantity right here. So we get minus V0 over L. This is a constant, this is a constant, so what we end up with then is a uniform field for this problem. The minus sign was to give us the correct direction for E, which in this case would be in the opposite direction to the vector z. That's why I put the minus sign in this direction here, in order to get J in the direction we would like. So let's look at our conclusions then. If we have a uniform J and a uniform conductor, we conclude that the charge inside, or the charge density inside, is 0. We concluded that the electric field inside is uniform throughout the conductor, and we can conclude that the potential increase as a function of distance is linear. It's increasing linearly with the distance z. And finally, we didn't prove, but I will mention that the surface charge density, which I represent by sigma q, remember that it's charge density, is not 0. And it's necessary in order to maintain the E inside uniform. So let me just point this out, that if we have a system like this particular conductor, where you may have this end here at V0 and this end here at 0, you wouldn't expect the E field to be uniform. You'd expect some curvature of the streamlines because of the geometry here. However, if you allow the surface charge to change, in other words, the negative charge to come down here and some positive charge to come down here, with the right distribution you can have that uniform E inside. We just want to point out that you will have the possibility then of a non-uniform surface charge density different from 0 on the outside. Another thing we can conclude, if we have the resistance go to 0, then if you look at our equations, this would be the case for a superconductor, the E inside does in fact go to 0. And you can think of it that there's no charge to drive, there's nothing to drive it, and so therefore we end up with a field that goes to 0. Let's talk about waste. Waste or not to waste, that is the question. Okay, we know that resistance results from the collisional transfer of energy from the charge carriers, which are being accelerated by the electric field, which we know is non-zero in the material, to the medium. Where current is flowing, say through this conductor or resistor, energy is lost. There's high loss of energy when it's not wanted. Well, what about when it's wanted? Well, that's when you're trying to heat something with electricity. Basically everyday things, stoves, toasters, hair dryers, water heaters, furnaces that use electricity. These all take electricity, convert it into heat. And some people would claim that that's a waste of energy. But more importantly, there are big issues of efficiency in doing this, and or are there better alternatives? By efficiency, most things, once you get the energy to the device, are fairly efficient because there's nowhere else for the energy to go but into heat. But it's getting the energy to the device that is costly in terms of efficiency. What about unwanted or wasted heat? Lights are becoming more efficient. Filament lighting is almost gone. It does in fact lead to heat, which you'd like to totally get rid of, is you'd like all your energy to go to light, and so far we have not been able to achieve that. The transmission losses are a big problem, and that's where it comes in on these issues of efficiency, because it does take energy just to get energy delivered. In refrigerators, you sure don't want heat. You don't want heat in computers, and you've probably heard of laptop meltdowns. Usually that's due to battery problems like the 787. Consumer electronics, even your iPhone and iPad get hot, and some people complain about that they get so hot that it's uncomfortable. The issue about transmission and generation of power has to do with thermodynamics. Power plants that burn coal or use gas are typically 30% efficient. And this is a result of just the thermodynamics, the second law of thermo. In order to work, you have to have a source of heat and a source where you dump the heat, and that's basically cooling towers. And the bigger the temperature between those two will give you more efficiency. But there's a limit on how hot you can go and how cold you can be in any kind of simple system. So if you're lucky to have, say, a lake or an ocean nearby, that will set this temperature. This is limited by the materials you're using to run the turbines and so on. So the bottom line is we pay enormously for wasted, unwanted heat. And we really have to address these issues when we're talking about green solutions to our environmental problems. So what you're trying to do is save energy consumption by making things more efficient or looking for other ways to generate the power other than burning coal or gas. In terms of dissipation, we've already said about how resistive media generate heat. This is just a repeat of what we've talked about before. Likewise, this equation here is what we derive to get something like I times V. Realize this is just the local version. J times dotted into E is like current times voltage. These two are related very closely. And these are the ohmic heating that we've talked about. We have this J dot E, and what we're saying is that that's being delivered to the resistor that's being heated. The E fields and the current densities, think of it as being a flow into the resistor. This is only schematic, but think of it as flowing from the source of potential to the resistor. In what I call the black box, we have to be generating the difference of potential in order for this to happen. And so you can think of J dot E flowing in this direction here in order to produce that potential. Well, that's going to cost somebody. It's going to cost money, and where does that money go? Well, it goes into the sources of energy that cause this flow of J dot E. So what are those? Well, there's batteries, there's mechanical devices, generators, there's thermal devices, which we've talked about, power plants. There's one that's not used very often, that's thermocouples. Nuclear, that is where the energy came from the universe. It's hand-delivered by elements that have the nuclei, which will decompose in order to give you the energy release. And then finally solar, which is in the form of radiation, so the IR and visible portions of the spectrum coming from the sun. And then of course the heating of the atmosphere is what causes the winds, which we can use to get energy. The bottom line is we don't get anything for nothing. We have to have these sources in order to do this step in the black box in order to get energy delivered to where we want it. Well, this is simpler to see. You're all familiar with the Van de Graaff. What we're going to be doing here is separating charge to charge up this dome. You might think of it as one or two ways. One is you charge this dome up and then turn off the motor. You've got this Q up here, and so the question is, can you use that to make heat, for example? The other way would be somehow you keep this running and generate some kind of current. Remember how it works. You have a source of charge, and then you have some motor which is turning here, and the motor is lifting charge up to the dome, which gets transferred, and then you come back down on this belt, no charge, and then do it again. This is the black box. So here's the black box schematically for the device. It's this system here where you plug it into the wall, you pay the electric bill to lift that charge up here. What is it doing? It's pushing this charge against the electric field that is accumulating on this because of this charge on the globe. Let me repeat. As you put more in charge up here, you have to push this charge against that electric field produced by this charge. That's the source of the energy requirement in order to charge this thing up. The more and more charge it gets, the harder it is to get this up, and so therefore your motor requires more current from the wall. So in the Van de Graaff, the motor does the work to raise or push the charge against the growing, increasing potential of the dome. You store energy via the capacitance of the dome. And so remember that's equal to Q squared over the capacitance, and of course the more charge you put on, the bigger the amount of energy. To create this potential energy, current, or J, had to flow up riding on the rubber belt against the E that is being generated by the Q. J dot E in this case is flowing from the bottom to the top. Now we want to recover that energy. If you short out the dome, so here's ground, and you take a wire and you put it right here, bang, without killing yourself, and you get all this current through this wire here, and it could have a resistor, okay, so that will give us some heat. You get all of the stored energy, which is equal to this quantity right here, you get it all back. And so all of that energy will go into heating that resistor. That's an example of the type of energy transfer where you do the initial step of creating a bunch of energy, then you take another step to dump it. There's another way that you could do this, and that is if you were very careful to attach this resistor and leave it here while this is running. Ideally, the charge here would just continue to flow through the resistor, and you'd have a continuous flow up to the dome, from the dome through the resistor. What you would then have is a generator which is creating a potential difference. So this has to be a higher voltage than this in order to get current through that resistor. And it's this whole process to maintain that current. You have to keep running this motor. Just think of it, if you stop the motor, you lose the current because the current would just basically discharge and you'd have no charge up here to give you a voltage to keep this going. So I think you see the point. You've got to have the motor. Got to be doing work in order to get useful current to do the energy transfer that you want. What is an EMF? This is a very important concept because it's the difference between a potential difference and an EMF. There's not much difference. The question is, how does it connect with the black box? Okay, so mysteriously you have a potential difference across a resistor, and we know that we'll get a current. So as long as you can maintain this, you'll get a current through the resistor. And we know that energy is being lost or dissipated in terms of energy per unit time, which is power. You'd have I squared R. And so the question is, do we have to maintain this? We must maintain it. If we maintain it, this driving potential difference, and remember V is defined per unit charge, we call that an EMF. I want to make sure that you understand this term electromotive force, an ancient term, and there really is no force. You can argue there's forces, but the main thing to think of it is that it's going to lead to a potential difference. What we're going to do then is bring in a source, and it's going to be this battery. So you put in this battery, which is then going to maintain the potential. An EMF is associated with some source of energy which can be converted into the necessary charge separation that creates this potential V. That's the black box. This is the black box. The battery is the black box. But it could be something else. To be useful, what does the battery do? It has to be charged if it's going to be the type of battery that requires charging, and that requires another EMF source. So mentioned before, the device that charges the battery could be chemical, mechanical, and so on. The other way is that you have a battery where you sacrifice metals to make ions in the solutions that are used in the battery, and these are eaten up to provide the EMF. And of course they have a finite lifetime, because when the electrodes are finally eaten up, you're done. I'd like to give you an analogy in terms of this EMF. So let's start with a flat table, and imagine that you take let's say a car, and you run it over a track or some path like this. You have no friction, and we're going to move it adiabatically, and I think you remember what that means. We have no acceleration. We're doing this very slowly. There's no energy lost or gained in the motion. If you stop the car, it stops moving the car, and there's no change in the energy of this system because there's no energy lost. What we have here then is a system where there's no change in elevation. So that's equivalent to maintaining this thing at the same potential. Let's go to the toy that we have here. It's a roller coaster. We start here and we end up here. Okay, so how do we do that? Well, I haven't ever seen this toy before, but it seems to have a mechanical device here which can lift a car from here up to here. We know that if we do that, we're going to have energy expended in order to do that. So we have to do work against gravity to generate this U, the potential energy that we have up here. So somebody or something must turn the crank. So somebody has to do the work. What that is doing, lift the car up here, that means this U, which is the potential energy that you have given the car, is produced by doing the work by turning this crank. If we take U per car, that's like the energy per charge, which will generate an EMF. If we're considering the analogy, it's U per car is like an EMF. With a bunch of cars, you could crank continuously and get a current of cars sliding down this track. That would be like, in this case here, if we just lift it once, that's like the Van de Graaff being charged and then discharged. If we keep that current flowing because we keep the motor on the Van de Graaff running, then we have a constant current and a constant rate of putting power into the system. Well, I'm probably overdoing this, but I think you see the analogy. I'd like you to look on the web to find out how a battery works. I'd like you to look at the chemistry of this. Just to remind you that there's all kinds of batteries. Don't forget the lemon battery. You take a zinc-coated nail and a penny, so you got copper and you have zinc, and you stuff them into the lemon, and you'll see a potential difference across here because of the chemistry that's occurring between the surfaces of these two objects. And believe me, these things will be destroyed eventually because of that process. Here's a 3-lemon battery, and you can see here it's giving out 2.7 volts. So you can light little light bulbs with that. What I'd like you to do is look at the chemistry of real batteries and realize what that chemistry is doing is separating the charge between the electrodes so that you can use it in circuits. So next time I'd like to begin our discussion of induction, which is basically generating EMFs with changing magnetic fluxes with time.